Right, so welcome everyone to this new episode of our lectures at your desk. It is my pleasure to introduce to you today Dr. Louise Breuval. She's an ESA Research Fellow at the Space Telescope Science Institute in Baltimore, USA, and she's also a member of the SHOES team. Her main work revolves around astronomical distance ladder and the direct measurement of the Hubble constant with Cepheid variables, a topic which, today, she will be telling us more about. So, Dr. Breuval, I leave the stage to you, and thank you for accepting our invitation to talk.
Thank you so much. First, I'd like to thank the organizers for inviting me to give this lecture. This is my favorite topic. So first, we'll talk about Cepheid variables. And then the second lecture will be about another distance indicator, the TRGB. So I think both are quite complementary. So we'll start with the Cepheids. I'll start with an overview and a reminder of how it works. And then we'll talk about how we combine the Cepheids with brighter distance indicators to measure distances to more distant galaxies. And then we'll talk about the systematics. So let's start simple with the simple question, what are Cepheids? Cepheids are pulsating stars. This pulsation is driven by variations of opacity in the atmosphere of the star. And these pulsations are extremely regular. The variations are not just brightness, but also color, temperature, and the radius of the star. So if you look at a Cepheid for a couple of nights, you'll see the light curve, and it looks like this. And it's you can look at it in different filters. The amplitude is bigger in the optical, and in the near infrared, it's slightly compressed. So this is the HR diagram, showing you the absolute brightness of the stars versus the color or spectral class. And the Cepheids are located in this region called the instability strip, along with other type of pulsating stars. Some of them have shorter periods, but overall they're the same family of stars. They don't always share the same mechanism for the pulsation, but overall they're the same family, and they're pulsating in this instability strip during this period of their life. So why we're talking about Cepheids today is because they're extremely useful as distance indicators. And why is that? So this has been discovered 100 years ago by a woman, Henrietta Leavitt. So she looked at a nearby galaxy, the Small Magellanic Cloud. And at that time, we didn't have CCD cameras. So she was using photographic plates. And she identifies some variable stars by looking at the same regions during many, many nights. So she compared these photographic plates between many different epochs, and she made a discovery. She showed that the log of the pulsation period was correlated with the magnitude. So all of these Cepheids or pulsating stars are located at the same distance to us in the Small Magellanic Cloud. So this means that basically two Cepheids, even in two different galaxies, if they share the same pulsation period, it means they have the same intrinsic brightness. So this is a really strong conclusion. It's really important for then measuring distances in the universe in general. So then for these two Cepheids of the same period, the difference in apparent brightness would mean a difference in distance. So if a star is twice as far, it will appear 4 times fainter. So here in her plot, it's a little bit different to what we do today. She's showing 2 different lines. One corresponds to the minimum of the light curve, and the other one is the maximum. But overall, the conclusion is the same. It's a strong correlation between log p and the magnitude. So this is now called the period-luminosity relation. I'll talk about it during this talk, during this lecture. I'll call it the PL relation or the Leavitt Law. So this discovery had a tremendous impact in astronomy and cosmology. 100 years ago, we didn't even know if there were other galaxies in the universe, or if the entire universe was limited to the Milky Way. So this was the great debate. And in 1929, thanks to the Leavitt Law, Edwin Hubble was able to measure the distance to a couple galaxies and finds evidence that the universe is expanding. So you've probably seen this plot before. It's the Hubble diagram with the distance on the x-axis measured from Cepheids and the velocity. So this is easy to do even at that time, just by measuring the redshifts. So today this plot is quite wrong, we know. So the slope of this relationship is h0, the Hubble constant, the expansion of the universe today. But because Edwin Hubble was not using the correct class or family of Cepheids, it was shifted. So there was an offset, and he estimated the expansion of the universe was much faster, much higher than what we know today. However, the trend was still correct. And the conclusion was still the same, that the universe is expanding. So all of this work, all of these discoveries had a huge impact in cosmology, and everything is based on the first discovery by Henrietta Leavitt of the Cepheid-Leavitt Law. And more recently, not only the universe is expanding, but the expansion is accelerated. This was discovered in 1998 by the Supernovae Cosmology Project and the High-Z Supernovae Search Team. They measured, this time they used type 1a supernovae, which are even brighter than Cepheids, to measure this accelerated expansion. So supernovae are also important. They're usually combined with the Cepheids in what we call the distance ladder. So they work differently, but they also have light curves. Basically, they're systems of stars accreting material from each other, and the explosion always occurs at the same mass and therefore at the same intrinsic luminosity. So basically what is done is the supernovae are calibrated with Cepheids, and then they allow us to measure the distance to other galaxies. All right, so basically in practice, how does it work? So the first step for measuring Cepheid distances is first the calibration. So you need to measure the absolute period-luminosity relation with known distances. So I know this might be confusing because we're talking about measuring distances, and I'm telling you, you need to know distances, but that's just to calibrate the absolute PL relation, and then you can apply it. So for that, you need first a sample of Cepheids with pulsation period that you measure from the light curve. You need to know their apparent magnitude also from the light curve. And you need to know their distance. Once you know that, you can calibrate. When I say we calibrate the PL relation, I mean you determine the coefficients A and B in this relation. Usually for the known distance, what we can do in the Milky Way is using the parallax method. This is quite easy. So because the Earth is revolving around the sun, and we know the distance between the Earth and the sun, you can look at stars during the course of a year, and the angle or the movement of this star with respect to background stars that don't appear like they're moving, then this angle gives you the parallax or the distance to us. So the closer the star, the more it will move during 1 year. So basically, this is this method that is used by the Gaia satellite. They measure the parallax of many, many stars in the Milky Way. And knowing these parallax gives you the information of the distance. All right, so then when you have this absolute calibration, then you pick a galaxy, you want to measure its distance. And what you need is, again, the pulsation period and apparent magnitude. And just by comparing absolute and apparent magnitude, it gives you the information of the distance. So it sounds quite easy, but there are many steps that I didn't show you, but they are also very important. Intermediate steps For example, first you have to identify the Cepheids. They don't come directly in catalogs. Someone has to find them. So for that, you observe the same region in the sky at least 10 times to detect the variability, and you get the light curves. You need to measure the pulsation period. So now it's quite easy to do with algorithms. But back at the time of Henrietta Leavitt, we're still not sure how the pulsation periods were measured. And then you fit the light curves to get the mean magnitudes. Usually what we use in these PL relation are really the mean, not the maximum or minimum. And sometimes we don't have full light curves, but we only have a few data points, for example, like this. So what we do is we use previously measured light curves in other galaxies, and we use them as templates to fit the light curves, to fit these data points. So it's not always easy, but these are super important steps in the measurements. All right, so I have prepared 2 notebooks to give you a short tutorials. Maybe I'll show them at the end if I have time, or I'll just give you the link and you can explore. It's really a few short exercises to show you the application of this method. So I'll just check the time, right? So now let's move on to the distance ladder. Now that you know how Cepheid distances work, the thing is, if you want to measure the expansion of the universe, Cepheids are not enough. They're not bright enough to reach the regime where galaxies are moving away from each other because of the expansion of the universe. You need to go further, and you need to use brighter objects, so brighter distance indicators. And these are type 1a supernovae. So there are many other distance ladder, as you'll see in the second lecture today. But in mine, I'll just focus on Cepheid and type 1a supernovae, which is the baseline or the best understood distance ladder. So there are 3 steps or 3 rungs. The first one is the absolute calibration of the PL relation, as I just described. So we use geometry. And this can be done in a few nearby galaxies, the Milky Way with Gaia, but also the Large Magellanic Cloud and the Small Magellanic Clouds. We know their distances from eclipsing binaries. And the other galaxy is NGC 4258. We know the distance from the motion of the water maser in the center. So all these are independent methods to get geometric distances. So once you calibrate the PL relation here in the anchor galaxies, you move on to the second step, the second rung, where you observe nearby galaxies with Cepheids. And at the same time, these galaxies must host type 1a supernovae. And using the Cepheids, you calibrate the brightness of type 1a supernovae. Of course, this sample is limited in size by 2 factors. The first one is that you cannot observe Cepheids very far away. At some point, they're too faint. And the second thing is there are not so many type 1a supernovae nearby. The rate is about 1 per galaxy every 100 years. So you'd have to wait a long time before you have a large enough sample. That's why this rung is the most limited in numbers of galaxies. So far, we have 42 supernovae in 37 host galaxies. So there are a couple of galaxies that host more than 1 supernova. And then finally, you move on to the last rung where we observe the supernovae, but the Cepheids are too faint at this distance. You cannot observe them anymore. So this regime has to be like far enough to avoid local gravitational interactions. For example, if you look at the first rung, these galaxies in the local group, for example, they're dominated by interactions. But if you look far enough, what you're really observing is the expansion of the universe. However, it also has to be close enough because you want to measure H0, so H0, H today, and not H of Z, so you don't have. So we try not to observe at too high redshift. So comparing then the redshift and the distances of these supernovae gives an estimate of the expansion rate of the universe, H0. So we're going to talk about H0 and the Hubble tension, although you probably heard of it in previous lectures. This is also another really nice video that illustrates the distance ladder. So it's basically same thing I just showed you, but Here, there's only one anchor galaxy, just the Milky Way, but keep in mind there are many more. I mean, there are 3 more galaxies on the first rung. Then the supernovae, you can see them exploding here on the second rung, and then the redshift here. So this is another way of seeing the distance ladder. But now, in scientific papers, it doesn't look like this. It looks more like this. So you've probably seen this plot before. It was published by the Shoes team. And it's exactly the same thing. You have the anchor galaxies on the first rung, the supernovae host galaxies here, and the Hubble flow. So I'm going to talk a little bit about the recent improvements in the Shoes distance ladder, because so we have done a lot of work to make the measurement stronger, the H0 measurement stronger, to reduce the uncertainties, to control the systematics. So I'm going to present a few details that we have worked on recently. I would say the most important thing in 2022 was the doubling of the supernova sample on the second rung. There used to be 19, and now there are 42. The histogram shows you the evolution of the number of type 1a supernovae here, and it has really doubled in the recent years. A couple of points that we really care about in the Shoes team is the use of the near infrared to limit the impact of dust. So we use one filter that's close to the H band, and we correct it for dust by subtracting a color term, V minus I. So if you want to know more about this, it's in the notebook I'm going to share later. And we fit simultaneously the 3 rungs with 5 free parameters: the Cepheid and supernovae brightness, the slope of the PL relation, gamma, the metallicity dependence. I have a couple slides on this later, and finally 5 log H0. So something we really care about is the consistency of the measurements across the different rungs. We observe the Cepheids on the first and the second rung with the same telescope, and that is the Hubble Space Telescope. And we even use the same camera to avoid any systematics. So of course, you can do this exercise with, I don't know, ground-based telescopes and other telescopes, different instrument on the second rung, and you might have very precise measurements. But at some point, you have to translate, or you have to transform these 2 systems, which introduces systematics. And that's what we absolutely want to avoid. So these 2 rungs really use the Hubble Space Telescope only. And the same work has been done for supernovae on the second and third rung by the Penthin Plus team to standardize and really use a consistent way of using these objects. So using this distance ladder, we have obtained a value for the Hubble constant. This is 73.04 plus minus 1.04. And just before we move on to the Hubble tension, I just want to highlight one more improvement we have done, especially on the Milky Way. So in my work, I especially focus on the first rung and the calibration here of very nearby Cepheids. And in the Milky Way, I told you about Gaia, but we came out with a new technique to improve the Milky Way calibration. So not only using Cepheids, but Cepheids in clusters in the Milky Way. So looking at clusters of stars, if there's a Cepheid inside that cluster, then you can take the average of all the parallaxes of all the members and get a much better estimate for the parallax of the Cepheid. All right, so cluster members are also fainter than Cepheids usually. And the thing is, Gaia is better at measuring faint stars than bright stars. I know it's tricky. We usually think the brighter, the better. But Cepheids are actually very, very bright, and most of them saturate with Gaia, so they don't always have a very precise parallax. So that's why cluster members are great. They're exactly in the best regime. They're not too faint and they're not too bright for Gaia. So if you average their parallax, they're absolutely perfect. So we have selected a sample of 17 of these cluster Cepheids that we have observed again with the same telescope with HST to be still on the same photometric system. And we have obtained a similar constraint with 17 Cepheids, a similar constraint as 75 individual Cepheids. So they're really way more precise, and it's a really great constraint. You can see here the period luminosity relation with, in gray, the individual Cepheids from previous works, compared with, in red, the cluster Cepheids. It's maybe hard to see if you're not used to looking at PL relations, but that's why I show you the small inset here where you see the uncertainty on the parallax. And here you can really see that the red ones are much smaller. So on average, 3 times smaller. Using that sample and putting it into the distance ladder, we have been able to reduce the uncertainty on H0 for the first time below 1 kilometer per second per megaparsec. I know it's a small improvement, but every improvement is good to take. So that's one method I've been working on. Now on the second rung, these are the Cepheids shown in red in the supernovae host galaxies. I know the supernovae are not shown here, just the Cepheids, but it's to show you they're really everywhere around the disk. And for each galaxy, there's a PL relation. I couldn't show all the galaxies, but there are many more. So this is the second rung. And so in the shoes analysis, what we do is we take the baseline, which is the final measurement, and every time we can, we change one single thing. So that's what we call the variance. So, and for all these variants, we see what can impact the value of the Hubble constant. So these are a few examples of Cepheid variance. For example, you can only use the optical photometry, you can use the most crowded galaxies, you can neglect the metallicity correction. Again, I'm going to talk about it later. You can assume a break in the PL relation, so a different slope. You can change the dust correction. And the bottom line is really that it's hard to get below 72 and it's hard to get above 74. And the dispersion of all these variants is included as a systematic in the measurement. And now, including all these improvements, the latest version, the latest value of the Hubble constant is 73.17 plus minus 0.86. And if you put it in the context of the Hubble tension, why is it so important to refine this measurement? So that's the expansion history of the universe with the Big Bang on the right and the present time on the left. So the method I just described, the late universe or the distance ladder, is what comes here. And the other method that you've probably heard about is using the CMB. And this assumes the lambda CDM model. So these two methods are really a end-to-end test of the lambda CDM model. So it's telling us that either there's a problem in one or two of these methods, or if there might be a problem in the lambda CDM model. So one thing I really want to highlight here, it's not a tension between two values or two measurements, but it's really a tension between the consensus among many early universe measurements and the consensus among late universe measurements. So although the Cepheids and supernovae are the most precise and the best understood and best calibrated methods, there are many more, and it's really, really important to cross-check them to validate their distance with independent methods, such as the TRGB. So that's what Deep is going to talk about in the next lecture. So you can, for example, you can replace the Cepheids by a TRGB or JGB method. And the type 1a supernovae can be replaced by the surface brightness fluctuation method or type 2 supernovae, etc. All right, so I don't think I'm going to do the tutorials now. I'll just go on with the lecture. But if I'll show this slide later, so you can find the link. Basically, there are two tutorials, 1 and 2. And you need to download these two data tables. So you just need these four things. And downloading these tutorials, you can just run them easily and just see the application. All right, so now I want to talk about two main systematics in Cepheid distances. The first one is the metallicity dependence, and the second one is the crowding. And in the crowding section, I'm going to talk about JWST. So first, let's look at the systematics in Cepheids. And by that, I mean we're looking at objects in nearby galaxies and the same objects in more distant galaxies. And the question is, are we really looking at the same objects, or are there any differences that we need to take into account? For the Cepheids, one of these differences is the metallicity, because we know, so the Milky Way and supernovae host galaxies here are quite similar in terms of metallicity. However, the LMC and the SMC in particular are way more metal poor. And so why is this important? Well, it's because metal-rich Cepheids are brighter than metal-poor ones. So you need to account for that when you measure their brightness. So we do that by including an additional term, gamma, in the PL relation. So it's not just simply A log P plus B, but it's also plus gamma, the metallicity correction, times the metallicity. That's something you can easily see when you plot the PL intercept or just the brightness of Cepheids as a function of metallicity. Here you have two methods. The first one is in yellow, orange. It's just looking at the Milky Way. As the Milky Way has a gradient of metallicity, Cepheids in the outskirts are more metal poor than Cepheids in the center. So you can use that gradient to infer the metallicity dependence, and you see that, that trend. So the slope of this relation is really the gamma term. So using this gradient, or you can take different galaxies like the Milky Way in red, the LMC in blue, and the SMC in green, and showing their intercept as a function of metallicity, you find again the same trend. So that these are two methods to measure the gamma dependence. So this metallicity effect has been measured by many teams, many methods, independent or not. And overall, in two filters, so MHW is more the infrared, and MIW is more of the optical. And there's a quite good consensus for this value between minus 0.2 and minus 0.3. The negative sign means that metal-rich Cepheids are brighter than metal-poor ones. And really, I want to talk about the impact of this correction for H0, because this has been a long debate of how does the metallicity correction impact the Hubble constant? So today, the supernovae host galaxies have similar metallicities. And so as you can see on the top x-axis, these are the values for H0 as a function of gamma. And within this range, there is very little change. So if you take the two extreme values, you get between 72.8 and 73.2. So it's a really limited range, so a very small change. But why this has been a debate? That's because before we had Gaia, before we used the Milky Way as an anchor, the LMC was often used as the only anchor, and the LMC was more metal poor. So at that time, yes, it was a really important correction, and it did have impact on H0. But now, not anymore, because we have more anchors, and especially we have the Milky Way. All right, so now that we know the value of this gamma correction, we also need to measure the metallicities, and that's not easy. For nearby Cepheids like the Milky Way and up to the Magellanic Clouds, we can measure individual spectra. However, in supernovae host galaxies, you cannot use that method anymore. They're too faint, they're too far. So we usually build metallicity gradients using H2 regions. So we don't use Fe over H, but this time we use oxygen lines. So the question is, are they consistent? Can we use these two methods? Well, actually they are. So this is a test comparing these two type of measurements within the Milky Way. So what you're actually seeing here is the metallicity gradient in the Milky Way. With in blue, the individual measurement, Cepheid by Cepheid, and in black are the H2 regions. So they really overlap. There's a good agreement. So I know it's maybe confusing, but the conclusion on the metallicity effect is really that it used to be a main systematic for decades because the LMC was the only anchor available at that time. But now we have more anchors, so it doesn't matter anymore. The exact value has very little impact for H0. It's still difficult to measure this quantity, the gamma term, because you need really good data and metallicities, and a large metallicity range is preferred. But now there's a good consensus on the value and on the sign, and it's been also confirmed by models and predictions. So it's pretty well understood now. All right, so that's all I had to say about the metallicity effect. Now let's move on to the crowding effect. So the crowding really is the effect of the surroundings of the Cepheids. If you look at, not in the anchors, but in the supernovae host galaxies, the more distant ones, when you look at the Cepheids with Hubble, you are often contaminated in the near infrared by the background or the nearby stars, and it's hard to distinguish the flux of the Cepheid from the flux of other stars. Now, with JWST, it's a whole different story. We can now resolve the Cepheid much better and separate the contribution of the Cepheid from that of other stars. So it's not really a systematic, it's a bias that can be removed. We used to correct, when we only had HST, we used to correct for that effect by adding artificial stars to the images and then remeasuring them to estimate the level of crowding. And this crowding really does produce a scatter in the PL relation, so it's more of a statistical noise, but it's we know how to correct it with HST, and now with JWST we can like really physically get rid of this noise. On the images, it really looks like this. So this is a galaxy where you see the Cepheid in red in the inner disk, and the level of crowding is really much higher than in the outskirts in blue. And in the period-luminosity relation, it looks like this. So the most crowded ones, so the ones in the disk, show a higher dispersion compared to the ones in blue. All right. So now what we do with JWST is we reobserve these galaxies and these Cepheids with JWST. You can see here the difference for the same star. Here, it's hard to tell how many stars are in the red circle, but now with JWST, it's much easier to say. So this is an actual example of a Cepheid observed with JWST. And we have been able to measure the PL relation in these galaxies. So as an example, the scatter was reduced by a factor of 2.5. We have HST in gray and JWST in red. And there's also really a good agreement between HST and JWST. So the main conclusion here is that the crowding was not a bias. It did not affect the H0 measurement. So it's hard to get time on JWST. So what we want to do is reobserve all these supernovae host galaxies. As I was saying, there are 42 supernovae here, and we have been able to observe only 24 with JWST. So I'm going to show more histograms like this. So the blue histogram is the full sample of 42 observed with HST, and we want to get as many as we can with JWST. All right, so this is another plot showing you the galaxies on the first and second rung observed by HST and by JWST. So first, the anchors, you have the 4 of them, LMC, Milky Way, NGC 4258, and the SMC. And the numbers on top are the deviations in terms of H0 compared to the baseline. So the baseline would be 73.2 based on the 4 anchors and all the supernovae. So that's really the HST main result. And you'll see a few variations depending on what anchor or what galaxies you're using. So everything in white is really just HST, and everything in color will be JWST. In blue, there will be observed by the CCHP team, and in red by SHOES. Both of them would be in purple, and some upcoming observations from the SHOES team in green. So now I'll show you the second rung. So these are all the galaxies, all the supernovae. On the second rung, some of them are still white, so only HST, and some of them have been observed by JWST. You can see them in red and blue. Again, some galaxies have two numbers. That's because they host two or more supernovae. Like this one has 3 supernovae. And again, the numbers are the deviations to the baseline by HST. All right. So I'm going to show again more histograms. So this was, again, in blue, the HST baseline, and in red is the sample used by Friedman 2024. They use one anchor, NGC 4258, so do we. And they obtain a Hubble constant of 70 kilometer per second per megaparsec. And the reason for that is not because there's no tension anymore, but it's just because of the selected subsamples. So there are 8 galaxies here, and just the selection of these particular sample gives you this distribution in H0. But if you look at the same galaxies with HST, you would get the same answer. Now, what we did in the SHOES team was combine all the galaxies that were available with JWST. So we had 24, again, just one anchor, but that's okay. And if you combine all these samples, then you get a much larger number of supernovae and much better distributed with respect to the HST baseline. And again, a very consistent H0 just by taking a larger sample. So this result was published a couple months ago in this paper by Adam Rees. So maybe Deep is going to talk about it again in his talk, because I know he was involved in this paper. So overall, the conclusion is that HST and JWST are in excellent agreement. Still, the HST baseline is the strongest constraint on H0. So JWST brings us some information, but not enough to say anything conclusive on the Hubble tension. And just be careful when you take some supernovae observed with JWST. Depending on your subsample, especially if it's small, you'll get a different answer. So H0 really strongly depends on the subsamples. All right, so we understand Cepheids really well now. There's been so much work done over the past decades, and it has really matured into the best established distance indicator. But there are a couple things that we can do to improve them a little bit better. So what's next for Cepheids? So there are possible non-linearities. Some studies have shown there might be a break in the PL relation, not necessarily in all galaxies or in all filters, but it's in some of them, possibly. There's also a possible dependence of the PL slope with metallicity. So far, we have only studied the dependence of the intercept, but not of the slope. As you can see here on this plot, it's hard to get a lot of long period Cepheids because they're much brighter and they have a shorter lifetime. So it's harder to observe them. They're more rare. We also want to have, as I said, Cepheids in the same homogeneous photometric system to avoid systematics. And again, it's hard to get telescope time. So if you want to use a space telescope, then you have to consistently apply for time and get as many galaxies as you can. We need to understand the effect of dust. Dust is not the same in all galaxies. In the Milky Way, as I said, Gaia is saturated for bright stars and unfortunately for many Cepheids. So we're waiting for Gaia DR4 to work on that and improve the parallaxes, and again, maybe refine the catalog of cluster Cepheids. As we know, it works really well. At the short period end, there's possibly a contamination from overtone Cepheids. They're another family of stars, of Cepheids that pulsate differently, and we really want to get rid of them to avoid any contamination. It's better to have well-covered light curves, but again, that requires a lot of telescope time. We need to observe more supernovae host galaxies with JWST to complete the sample. And something else I've been studying is the effect of depth in the Magellanic Clouds. So this really is important in the LMC and SMC, not in other galaxies, but in the Magellanic Clouds. These galaxies are quite elongated, and there's a strong effect depending on what sample you use. So the radius of the sample gives a different PL scatter. So it's important to find the best region to study. Anyways, and there are way more things to study on Cepheids. They're very complex, but very interesting objects. And hopefully in the future with HST, JWST, Gaia, Roman, and so on, we can understand even more these beautiful objects. And I thank you so much for your attention, and I'm happy to take any questions.
Hello, thank you very much for your talk. I am a PhD student on cosmology. I have a doubt of your talk. You said that, for example, the best measurement about Hubble constant is the light time Hubble constant measurement, like with Cepheid. Which advantage does the Cepheid have with respect to high redshift measurement like CMB, for example?
Oh, yeah, thank you for your question. Yeah, I'd say the main advantage of Cepheids over cosmological measurements is that they're really nearby, that their physics is well understood, and everything is really empirical. So there's no models. Because the physics is really well understood, we can only use observations, so only telescopes and using the same telescopes consistently. So you can really get rid of any contamination, any assumption. So it's a really, I would say, a pure empirical measurement. And that's what I think makes the strength of Cepheids. And they're really bright.
Okay, thank you very much.
I have one question. So you mentioned all these parameters that are determined essentially by a fit. But if one understood the astrophysics at play in the stars correctly, wouldn't it be possible to also calculate some of those parameters from first principles? And are there any plans to maybe do that?
What other parameters are you talking about?
I mean, like the parameters in this PL relation.
Yeah, so we're measuring both parameters of the PL relation. These are the two parameters that we measure in the PL relation, A and B. They are empirically calibrated and measured. And the other parameter in the PL relation is gamma, the metallicity dependence, and it's also well understood and well measured empirically. Can you elaborate on your question? I'm not sure.
So the question would be if from the theory of how these stars work, it would be possible to deduce A, B, and gamma from first principles and then compare with the values from the fit.
Yeah, sorry for the confusion. Yeah, of course. Yes, this is something we can do already. There are theory papers on the pulsation of Cepheids. There are models that try to reproduce the pulsation and the behavior of the Cepheids as stellar objects. And it's also so well understood that you can predict these numbers and they're actually well reproduced. So there's really good agreement between what we measure and what we predict. There's a paper well, it's not submitted yet, but there's a paper coming out in the next few weeks about that, including the metallicity dependence. There are some papers by Richard Anderson working on the models of Cepheids, and it works pretty well. So you're right, yeah. it's now possible to measure them theoretically.
Okay, interesting. Thank you.
Maybe I can share the tutorials, the notebook. All right, so the first exercise is really the calibration of the PL relation with Gaia. So first we import a few packages. If you download the data, here you need to update the place where you copy paste the data table. Then you use this one, the RIS 2021 table so you'll see it's a list of Cepheids in the Milky Way. You have the log P, then you have a few filters, so F555, F814, and F160. This one is the near infrared. And the one we're really using is this one, the MHW. So it's the near infrared corrected for dust. And the other information that's really important is the parallax. So PLX DR3 is Gaia parallax. So this is the form of the near infrared color corrected magnitude that we're using. Here I'm telling you a bit more about the correction we need to apply to the parallax. So you cannot use them directly, you have to correct them for some effects. And then you derive the absolute magnitude using this equation, and then you plot the PL relation. So that's really easy, it's just straightforward. And then you fit a straight line to these points, and you get the beautiful PL relation in the Milky Way. That's your slope, and that's your intercept of the absolute PL relation. And that's what you want. So then I'll go to the second tutorial. It's the application of this. Now we measure the distance to another galaxy using this calibration. So here you're going to do the same, use this, you update this. And this time you read the other data table, RIS 2022. And this is a really long list of Cepheids in many host galaxies. So you can pick one. I picked this one, but you feel free to take any other galaxy you like. And you build the color corrected magnitude. And here you use the same slope. So something really important here is if you use the calibrated PL relation to measure the distance to another galaxy, you need to use the same slope. So you really have two parallel lines, two parallel relations, and the difference in intercept would give you the difference in distance. So it's basically the same exercise. Here's the PL relation you get in this one. But again, feel free to test it in other galaxies. It's more scattered. It's not as nice as in the Milky Way, obviously, because it's more distant. And using the same slope, you get this intercept. And then you just apply the equation to get the distance. In our field, we use distance modulus in MAG. But if you prefer in megaparsec, you can also get the distance in megaparsec. So yeah, that's it. So feel free to play with this data. It's really nice. Especially this table has really a lot of different galaxies. So you can really see a lot of different PL relations in different galaxies.
I thank you again, Dr. Breuval. That was a very nice presentation. Thank you also for the notebooks.
Thank you so much for your attention.